Okay, welcome everyone, and thank you for joining us today for this series of webinars on how electron diffraction is transforming research across the fields of materials, life science, and chemistry. My name is Fraser White, and I'll be your host today. It's my pleasure to introduce today's presenter, who is our product manager for electron diffraction based in our European offices near Frankfurt. Robert's driving the development of our Crystal Lab Synergy ED and came to us from Hamburg with vast experience in electron diffraction instrumentation. So as some of you may already know, this is the second webinar in this series of 6, and today you'll learn more about the history of electron diffraction, the physics behind the technique, and some of the challenges we've faced along the way and how they were overcome. Before we get to the main presentation, I just wanted to inform you of a few quick items. So if you have a question throughout the presentation, please ask using the Q&A button, and these will be read out at various points throughout the webinar as time allows. Any unanswered questions will be responded to after the session. And where applicable, please try to include the slide number if you can, so that we can more easily understand the context of your question. The chat is open, but please note that we'll be using it to paste links throughout the presentation. And if you do ask questions there, we might miss them as we won't be expecting to see them and they might get lost in the history as new messages appear. We are recording this webinar and the recording will be available from tomorrow. If you have any trouble watching the presentation live, we recommend that you catch up via the recording as it's unlikely we'll be able to resolve technical problems during the webinar. The recording for the first webinar is also already available on the series site, which I'll paste into the chat in 1 second. Okay, so lastly, if you haven't already, we'd encourage you to register for the whole series using the link I've just pasted as well. And with that, I will pass over to Robert. So thank you for your patience, and please take it away when you're ready, Rob.
Thanks, Fraser. Hi, everybody, and welcome to this episode of our webinar series on electron diffraction. Thanks for the introduction, Fraser. Before we get started, I'll just give you a quick overview of the agenda of today's presentation. So we will start with a bit longer introduction today about the fundamentals and the history of electron diffraction, how we do it today. After that, I will talk about some details about practical aspects, how we can practically implement electron diffraction and how this is done in the lab and specifically in our electron diffractometer, the Synergy ED. I'll then explain some of the specific properties of electron diffraction along the lines of some use cases that we had with our customers and also more generally. And finally, give a bit of an outlook about ongoing developments with electron diffraction and where the whole field is evolving. So let's start with the first section, how did we get here, the fundamentals and history of micro-ED. So this slide I have taken from the previous episode of our webinar series from Pierre, which illustrates the principle of single crystal diffraction in general. So conventionally, you do it with X-rays. So you have a monochromated and collimated X-ray beam, you shoot it on a crystal, and while you're rotating the crystal, you collect the intensity of different diffraction spots, and then computationally via Fourier transform and injecting computationally derived phases, you can end up with an electron density map and fit a molecular model into that. Now, what if we replace those monochromated X-rays with electrons? So in this case, if we assume that we have typically 200 kilovolt accelerated electrons, we can use crystals and rotate them the same way in the beam and get same kind of intensities in the Bragg spots, just that the crystal will now be much smaller. It has to be less than a micron, and we'll see in a second why. The other only relevant difference downstream from this is that you're not actually measuring the electron density, but the electrostatic potential. Also, this has some subtle consequences, as we will learn later on. Let's look a bit into the physics and how this differs between the X-ray scattering and the electron scattering. So as many of you will know, X-rays scatter elastically from the electron density around each of the atoms in your specimen. This is a bit different for electrons. Electrons do their elastic scattering by being deflected from the Coulomb potential inside the specimen. So you have the electrostatic potential field, which exerts a force on the electrons and deflects their trajectories. And in fact, the cross-section of this process is up to 5 orders of magnitude larger than this one. And this means that for electrons, you can get diffraction signal from submicron crystals. And that's the key feature of electron diffraction compared to X-ray diffraction. It also means that these submicron crystals are also required, because if you have larger crystals, they will essentially act as a beam stop just because this interaction is so strong. And another detail that you can derive from this is that this electrostatic potential, which is sensitive not only on the electron shell around nucleus, but also the nucleus itself. And this is the formula for the atomic form factor if you do electron diffraction. So this electron form factor is proportional to the charge of the nucleus. So here you have the atomic number, but then also the electron shell. So here you have the form factor of the X-ray. And the electron diffraction form factor hence sits somewhere in between X-ray and neutron diffraction in that it sees both the nucleus and the electron shells. Another more subtle but as important detail is that you don't only have elastic interactions between your beam and your sample, but also inelastic ones. And those are generally detrimental because they will damage your sample by depositing energy into it. And for X-rays, the ratio between inelastic and elastic collisions is quite unfavorable, and they deposit a lot of energy into your sample. So you damage your sample quite a lot for each useful photon that undergoes an elastic scattering process. And while for electrons these numbers aren't that great either, they're up to 3 orders of magnitude better when it comes to how much damage you have to incur on your sample to get a certain amount of information on your structure out. And that makes electrons again compatible with getting good diffraction data from small crystals. And another property of this mod beta formula that relates those atomic form factors is that the scaling of these form factors and of the total strength of interaction with the atomic number is a bit different between X-rays and electrons. I don't want to go into too much detail here. There are quite interesting features you can observe. There's a nice paper explaining this in more detail. And I should say that Fraser will always paste all the references that I'm giving, there are quite a lot of them, into the chat. Can highly recommend this review paper. I just want to say that the scaling of the interaction of electron scattering with the atomic number is weaker than for X-rays, which means that the relative visibility of light atoms with electrons is higher. And as we will see later on, this is quite useful when it comes to detecting light atoms and specifically hydrogens. So if we want to now see where electron diffraction stands within the context of other techniques, well, of course, we have to compare it to single crystal X-ray diffraction. And single crystal X-ray diffraction, just in general, is restricted to what I would call the visible crystals, so crystals that are larger than 1 micron. And once they get smaller, then even with synchrotrons, it'll be hard to extract useful signals from a single crystal. If you have powder X-ray diffraction, you can, of course, go to as small crystals as you like, but you only get a much less powerful data. You just get a one-dimensional spectrum. And a lot of modeling is now required to get structural information out of this. You'll have line shape that you have to characterize, preferred orientation maybe. And if you have complex mixtures of polymorphs and impurities in your powder, you can maybe identify them, but really figuring out what's in there can be prohibitively complex. And with electron diffraction, you have sort of the best of both worlds. It's a single crystal technique that acts on each individual powder grain in your sample. And now one thing that's, I think, not discussed a lot, and a question we sometimes hear is, why weren't we always doing this? If that's so great, why is now electron diffraction a recent hype, as it seems? And this is, in fact, a totally valid and an interesting question, because electron diffraction is a really old technique. It's 100 years old around. So why haven't we been using this for structure determination for a long time? And for this, I would like to explain what is typically considered under the name electron diffraction. And this is shown here. So typically you use an electron microscope, and then in that electron microscope, you tilt a crystal along two axes carefully such that the Ewald sphere, and the Ewald sphere with electrons is actually not really a sphere, it's a plane because of the short wavelength, and that this Ewald sphere is aligned with low-lying zone axis. So what you get are diffraction patterns which have a very high degree of two-dimensional symmetry, as shown here along those zone axis patterns. So they look very beautiful. You get the lattice constants from this very nicely. But getting structures out of this is very, very tricky, because if you compare this observed pattern to a corresponding calculated pattern, you see that the intensities look totally differently and they're all messed up. You can also see that systematic absences are totally violated. And the reason for that is that multiple scattering due to this strong interaction leads to dynamical diffraction effects. And this dynamical diffraction due to multiple scattering shows up in that the intensities of the Bragg spots are not anymore proportional to the square of the structure factors, which is the underlying assumption in this calculation. So using this conventional approach, it was always thought that it's pretty much impossible to learn anything about the structure from this kind of data. In fact, if you look at how these Bragg spot intensities scale with the thickness of a sample, then even in the case of lysozyme, which is nothing particularly heavy, already at around 100 nanometer, you start seeing strong oscillations that depend on the order of the Bragg spots you're looking at, and that are even selective on Friedel mates, which is quite interesting because, as we will see later on, this means that we can solve absolute structures. Still, it has been demonstrated that it's possible to solve structures from this, and this has not been recognized a lot in the structural science community, but as early as in the 60s, this was done by Weinstein in Moscow, and then later on by several other groups, for example, in Stockholm. And structure solution was absolutely possible, but not exactly straightforward. So what happened then? Why do we suddenly see this surge in electron diffraction? And this was due to a paradigm change that happened around, let's say, 20 or so years ago. And this was actually realized by considering that these conditions at the zone axis are the worst possible conditions to get good intensities for electrons. Because you have so many reflections excited at the same time that if an electron ends up in some of those spots, it can have taken a lot of different paths there via multiple interactions, and they interfere in complex ways, and this messes up these intensities. So the realization was made specifically in the group of Ute Kolb in Mainz that if you collect electron diffraction data like you would for X-rays, which is just rotating a crystal freely in the beam and staying off those zone axes and just get patterns like those, which are much more random and sparse, you restore data that are much more kinematical and can be used for structure solution straight away. And this was a huge game changer. Now, one thing that's very, very interesting and peculiar is that the exact same thing has been recognized and realized in protein crystallography. I would call this, let's say, some sort of convergent evolution, because as early as in the 70s, there was seminal work by Henderson and Unwin, later on also by Gonin and others, on 2D crystallography. So solving structures, especially of membrane proteins in 2D crystals from just a tilt series of crystallography. So again, tilt series, just like realized here, but it was always assumed that this would only work for those thin protein crystals of only a single or maximum a few layers. But it turned out that nobody really tried with 3D crystals until some people did, especially in Tamir Gonin's group at HHMI, and also Jan-Peter Abraham's group in Leiden, and later on in Basel, and then also in Stockholm and other groups. And when they tried, it was actually find out, no, this actually works. And those dynamical effects, especially in the case of proteins, have always been over-exaggerated. And after this realization, we now have this pretty much same technique derived from two different directions. And this is, in fact, the reason why sometimes you see this modern electron diffraction labeled as 3D ED and sometimes as micro ED. It's more or less the same thing. It just comes from different communities. There's been a bit of method evolution when it comes to data collection. Initially, those rotation data were taken in a stepwise tomography. A bit later on, it was realized that adding beam precession to this increases the data quality because you integrate over the spots more nicely and more completely. And then even later, continuous rotation schemes were realized where, as in X-ray modern diffractometers, the crystal just rotates continuously and the data are collected in a shutterless way. Now, the latest new schemes focus on automation. So usually in your TM or diffractometer, you will have a lot of small crystalline grains, and automation schemes will then allow you to find them automatically and collect diffraction data from many of them because electron diffraction collection is really fast. And then automatically associate each of those data sets to different structures which just might be present in a mixture and solve data from them. So in this presentation and also in our Synergy ED diffractometer, we're focusing on this continuous rotation technique with an increasing focus on these automations. On the other side, also the analysis techniques have improved for electron diffraction. So classically, one would always, even for these electron diffraction data taken in this rotation way, one would apply this kinematical approximation, just saying, these intensities will be close enough to the structure factors. And it turns out that for ab initio structure solution, that's absolutely good enough. And the standard codes for that just work. Still in refinement, the R values, specifically R1, will not go down to the level as you would expect from X-ray crystallography. And that's not because the data is bad, that's just a systematic effect, because for electrons, this is just an approximation. This is just approximative, it's not an equal sign. However, even though this residual of an optimization will remain high, it doesn't mean that the position of this minimum would be wrong. So the structures can still be highly accurate, even though you have the systematically worse R values, something that really needs to be understood. On the other hand, if you really want to get the best out of your electron diffraction data, you should explicitly model those intensities using a full dynamical theory that takes into account multiple scattering. And especially the group of Lukáš Pelatinos in Prague has done seminal work on this with a breakthrough paper in 2015 to explicitly model those intensities. And if you do that in your refinement, you get much improved maps with better visibility of light atoms. You get the absolute structures, as you will see later on, and also these R values recover almost to the level of single crystallography. So, of course, then the story went on quite a lot on all kinds of different crystals and applications, and I don't want to go into too much detail anymore, but this is a list of recommendations for review papers, and Fraser will post those into the chat. So as a bit of a recap, what is micro-ED/3D ED? The basic idea is you replace X-rays in single crystal diffraction by electrons. You get stronger interaction, lower damage, means you can use smaller crystals. This modern scheme has been developed in the 2000s and 2010s, and because it was developed in a lot of places a bit in parallel, there are also a lot of names associated with it, though 3D ED and micro-ED basically are now the ones mostly used. It has been applied to pretty much everything that's crystalline. And now, and this will lead us to the next section, so far, these measurements have been conducted on modified, more or less modified transmission electron microscopes, which poses the problem that this limits the user group to people and research groups who are skilled both in electron microscopy and in crystallography. And this is quite tricky because the paradigms of how these instruments work are very different. So now dedicated instrumentation is becoming available, and this is yet, I would say, another paradigm change to make electron diffraction accessible to a much wider audience. But before I go into detail about these practical aspects, are there any questions so far?
Yes, so we do have a couple of questions. So the first one is maybe more of a technical support question. If you can't answer it, then we'll pick it up later. But we have ED frames in CBF format, but Chrysalis Pro can't open them. What might be the reason? I suspect that might be one we want to pick up later, but if you have any
Yes, I
initial
would say so.
thoughts, okay. And the second question is, you mentioned that the strength of dynamical effects was overestimated. Why is that, and what was missing from those estimations?
That's a very good question. So there are some conjectures about this. And wait, yeah, I actually have something here even. So two of the conjectures are that what was actually assumed for these estimations of dynamical effects is a too perfect crystal, much more perfect than it ever would be in reality. Namely, a crystal that has absolutely no mosaicity. So that means that the diffraction from the entire crystal, the diffraction signal, can interfere coherently with each other, giving rise to strong dynamical effects, where in reality, you have mosaic domains which diffract more or less independently. So the effective crystal size is smaller, restoring more kinematical conditions. The other aspect that was largely not incorporated is inelastic scattering, which also decoheres the electron beam and suppresses dynamical effects. So the current understanding of this is still a bit incomplete. This is improving quite a lot at quite a pace right now, but these are two factors which have been forgotten, or let's say disregarded in this estimations.
Okay, that's all of the questions for now, so please continue.
So let's continue with the practical aspects. This is just our electron diffractometer, and as I mentioned already, this one is just made for crystallographers, so even a wider audience, structural researchers, not specifically for electron microscopists. It has a highly optimized and integrated hardware and a software just for 3D ED or micro ED, and it provides very seamless and automated workflows all the way from instrument control, sample screening, all the way to structure solution. And I want to explain electron diffraction a bit along the lines of how you do it in the Synergy ED, but this also applies to some extent to other instruments where you would run electron diffraction on. So a few things to keep in mind if you want to do electron diffraction, especially if you come from the X-ray world. These nanocrystals are invisible to light microscopy because they're just too small. So you have to do the screening and searching for good crystals inside the diffractometer itself using electrons. Next, the electrons only will pass vacuum. They will actually be immediately absorbed in air. So you need to have the diffractometer in vacuum, you need a sample transfer system to get the samples into vacuum, and you need to protect your samples if they're vacuum sensitive, for example, because they hydrated and would dehydrate. The radiation doses, I mentioned this before, are relatively really high in electron diffraction because you want to extract all the signal you need from a tiny volume. So you cannot afford to waste any electrons in detection. You need the most sensitive detector you can get. And in your implementing your control system, you need to be always cautious about not applying too much dose. And then you have, because you essentially load a powder, you have thousands of crystals in each specimen. The nice thing is that you have multiphasic and mixed samples. This becomes totally tractable because you can measure them separately. But also it means that automation and big data processing are a much bigger topic for electron diffraction than for X-ray diffraction. I don't want to talk too much about the practical workflow of electron diffraction because my colleague Jessica is going to give the next episode of this webinar series. Fraser is pasting the link into the chat. Just very briefly, what you do for an electron diffraction experiment is you put a bit of a powder on a grid, and then you put this grid, which is just the same as for electron microscopy, 3 millimeter in diameter, into the vacuum of the diffractometer. You switch the diffractometer to a screening mode, which is a real space mode with, compared to an electron microscope, very low magnification and very, very low dose, so you don't damage your crystals. And in this, you can just find interesting crystallites that would be worth your attention, and then collect data from each one of them. You can collect up to a full data collection with an almost complete data set. within less than 2 minutes from each of the grains. So this is roughly how it works, but in Jessica's webinar, you will learn much more about it. Now, what is inside an electron diffractometer? Let's just have a brief look at that. In our Synergy ED, we are collaborating with Deol, a leading manufacturer of electron microscopes and electron beam instruments in general. They also happen to be almost next door neighbors of Rigaku in Tokyo. So we have a beamline operating at 200 kilovolts, which has these real space screening capabilities that we need to find the crystals in the first place. We have a zoom system sitting behind the sample, which allows to set the detector distance over a very wide range without physically moving anything. We have a quite complex condenser system that allows to change the illumination conditions a lot, like many of orders of magnitude in terms of illumination strength, for example. And we also provide some means for elemental analysis using X-ray spectroscopy straight built into that same instrument. The detector is the Rigaku HiPix ED. It's the same detector that sits also on our X-ray instrument, so it's single electron sensitive, has no background, is fast and shutterless. It's pretty much all you could wish for crystallography. All of this instrument is operated directly via Chrysalis Pro, our usual crystallography package at Rigaku Oxford Diffraction. It does really everything: instrument control, automation, screening, collection, and data analysis. And everyone who's used the Rigaku instrument before should feel straight at home on the Synergy ED as well. And we have a sample stage that provides you with a lot of different options how to put your sample into the diffractometer and give you different options for sample environments. So how does that work? So the goniometer is actually outside vacuum. What you do is you put those sample grids inside this transfer rod, inside these holders. And then this holder is transferred into the vacuum through an airlock. And throughout the whole screening and measurement sequence, this sample and this holder remain a monolithic unit, as you see here. So sample is then rotated using the goniometer. And during the continuous rotation, we have continuous readout from the detector into diffraction frames. And then ideally, you will see that these frames are being processed or during data collection. And in the simple cases, you can even have the structure solution before the data collection has even finished. So anyway, the fact that this the sample always will remain on the holder as a monolithic unit means that you can put a lot of smarts into those holders, like cooling the sample from a dewar that's mounted here, like having electrical connection for it for heating to high temperatures, motion control. You can have tubings for gas and liquids that you can introduce into some sort of microenvironments here. I'll just talk a brief little bit later on about this. The most important system for this is a cryotransfer. So here you see one of those sample transfer rods where you put the sample on the very tip here, and then you have this rod with a dewar on the back. And if you have hydrated samples, the way to protect them from vacuum is then to cool down this tip, plunge your sample into liquid nitrogen or liquid nitrogen vapor. And then before transferring this whole rod into the diffractometer, you can actuate using this knob a shutter that will build a small microatmosphere around the grid here that has just dry cold nitrogen, and that will protect it during the few seconds that you move this into the diffractometer. And this makes a huge difference. If you have, for example, a structure like this one of hydrated sugar, you will see that if you just do a normal transfer at room temperature into vacuum, then the vacuum will dehydrate it. And if you have cryotransfer, it will just keep its hydration. And I would estimate that for roughly half of the samples that we are measuring in the lab, we need this cryotransfer capability. Do you have any questions about those practical aspects?
Yeah, so we have a few questions. Another couple just popped in. So First question, I know it's not what it's designed for, but could Synergy ED be used to observe grids for particle density for single particle analysis? Not to collect imaging data, but just to get an idea of how the grid looks.
Well, yes, I would say so, because if you just want to check for loading density for single particle analysis, you would typically use relatively low magnifications. And even though the electron optics in the Synergy ED is not built for high quality real space imaging, it should be enough it should be enough to assess loading density. I wouldn't 100% promise it. I would have to make a bit of a, let's say, back of the envelope calculations about it, but it should work.
Okay. Next question, kind of coming from the opposite side, can you look at grains in higher resolution on a dedicated diffractometer like you can on a TEM?
You can to some extent. So the typical magnification, we have what we call a high resolution mode. That would make any microscopist laugh, what we call a high resolution mode. But we have something like this, what you see here. So this is a 500 nanometer scale bar, where you can see the morphology of a typical grain of the typical size range for electron diffraction very nicely. So we have this mode, it's fully calibrated and automatically sets the illumination conditions and so on the Synergy ED. So we do have that. And if there are specific applications needed for that, we can also tweak it to even zoom in higher. This is just, we find the most useful one. So it will not be as high resolution as a TM, but it still goes up quite high. Of course, for those images, you'll have to impart a much higher dose. Then also the dose that you have to put on your sample gets into the order of magnitude of a TM. What you also see on this slide, by the way, is other types of what we call post measurements, which would also be elemental analysis as well as tomography measurements, so observing the grains while they're being rotated.
So that answers one of the other questions that came in. Thank you to that person who asked. Another question is, is there no way to prevent multi-diffraction with ED even using a goniometer with super high precision? I guess they mean diffraction from multiple grains at the same time.
Let's say if you had an infinitely great goniometer and a very, very small beam, then you could at least minimize those effects, I would say. Practically for almost all applications that we're looking at, it's not a limitation to find grains that are spaced from each other by, let's say, at least 1 or 2 microns, which matches quite nicely with typical sphere of confusion you can achieve with a realistic goniometer. If you want to go smaller than that, you'll again have to resort to those stepwise techniques, like in the older days, like you see it here. Because here you can actually take a diffraction snapshot, recenter your grain in the screening mode, and then take the next diffraction snapshot or add beam precession to this. This is possible, but comes at quite a penalty of a very slow measurement compared to continuous rotation and also a much higher radiation dose.
Okay, there are still 3 questions, but I think in the interest of time, we'll move along and maybe we can pick those ones up offline.
Okay. Then let's continue with the next section. Where does it help us? Some use cases and success stories that I think will highlight where electron diffraction has been useful at Rigaku and for our customers. I should say that we have now almost 60 peer-reviewed publications with Synergy ED data, and some of them really high-ranking journals. And this number is now quickly growing as we have more and more Synergy EDs out in the field. Let's start with a polling question. So the question is, if you think about electron diffraction and all that you may know about it, what class of samples do you associate most with this micro-ED technique?
So I've launched a poll. The possible answers are proteins and peptides, pharmaceuticals and small organic molecules, minerals and ceramics, natural products, framework materials like moss, battery materials, or if you think of something else, we've given you another option and you can feel free to paste it into the chat if you like to tell us what you're thinking of.
Okay, so
So it's still
I
coming
think
in quite thick and fast. So I'll let it run for a little minute,
okay.
but it looks like the pharmaceuticals are winning by some way.
Yeah. So the pharmaceuticals and the framework materials, I think, are now leading the pack.
Yeah. Okay, I think I'll stop it there.
Okay. So pharmaceuticals and small organics actually made it up, and then framework materials as a runner-up. And I would say this quite reflects with also what we see when we get requests from customers and from collaborations. I would say at the moment it's even framework materials may still even a bit more of the common use case, but of course in total pharmaceutical and small organic molecules may just be the larger field. Um, but I think this reflects quite nicely what we see, and I will show you some examples for all of this. I won't talk much about proteins and peptides. That's super exciting, and it's been one of the original use cases for microED, of course. But this is a huge topic and would lead us a lot into sample preparation techniques, and that we would just like to save for another time. Okay, very interesting. Thank you. So if I go to the different use cases of electron diffraction, the most straightforward answer, what do you need it for, is just, well, crystals that are too small for single crystal X-ray diffraction. And thanks to the stronger and more gentle interaction of electrons, you can just solve them. And this is something you can observe all the way through a lot of different sample classes that like we see here. Like here's a one-to-one co-crystal that we see here. We see organometallic. This is what do we have here? There's another organic molecule, and here's something totally exotic, a nanographene, which is a very complex layered structure. And all of this are just, it's impossible to grow crystals from them that are larger than, let's say, a micron, and electron diffraction can just solve them. For inorganics, like here for this catalyst, similar situation for minerals, for example. It's just impossible to grow larger crystals, of course, and you often have multi-phase examples, and getting the phases out from powder diffraction patterns is often prohibitively difficult. And with electron diffraction, because you screen this grain by grain, you find it out straight away. You have a similar situation very often with especially pharmaceuticals, where it's often hard to recrystallize your API into larger crystals or get very poor diffraction quality. And also polymorphism is rather the rule than the exception. And in this particular study, it was really possible to grow crystals from a certain polymorph of this API. And then it was also found to some extent why this is the case. And that's because this form 7, in fact, consisted of two different polymorphs that were only possible to distinguish in electron diffraction. So new polymorph was found here. And of course, there are also cases where just the structure is impossibly difficult, like this one. I cannot even properly pronounce it and don't know much about the chemistry, but I find it very, very impressive that this can be solved at all. And I just quote from this paper here, which was the first published Synergy ED paper, and we're very proud of this. It was from the group of Neil Champness and Birmingham and Nottingham collaboration. So a diamond light source. The refinement was highly challenging, requiring a large number of restraints and for some atoms to be placed in calculated positions prior to refinement. In addition, we were unable to locate or even identify anions in the X-ray structure. So it didn't go too well. For electrons, the resulting structure confirms the overall arrangements and verifies the adoption of pi interactions between the PDI and the macrocycle. The close proximity of these groups is significant. To our knowledge, this is the first crystal structure determined for heterorotaxene by either X-ray or electron diffraction. So this was one of the first use cases for a very difficult system where you've seen that even with synchrotrons you don't get far, but if you use very small crystals with electrons, you can get a nice solution. And a typical case where you also observe this are natural products. They are usually very fragile. They have poor crystallinity. You only have tiny quantities available, but they are totally sufficient for electron diffraction. And you need a lot of screening to even find something that's crystalline. So this is also a promising upcoming field for electron diffraction. And now I mentioned already porous material research. I don't want to talk too much about this because in another episode of our series, Ross is going to talk much more about metal organic frameworks and how micro-D is not only becoming, let's say, one among the tools of MOF research, but really you could say there's a bit of a micro-D driven research because it allows new types of synthesis which previously would have not been feasible because you could never grow crystals that you could characterize in the first place. But now with electron diffraction as a standard tool available, you can explore synthetic pathways which just give you the small crystals that you can still understand. And of course, there are a lot of practical use cases for this, for gas absorption and separation materials. This is not limited to MOFs, but also COFs, CIFs, 1D and 2D structures. And we get a lot of publications of this kind, and data from the Synergy helps really a lot here. Now, specifically for those porous materials, it's quite relevant that we can do those measurements in micro-ED, not only in vacuum, but also in cryoatmospheres and gas atmospheres, to some extent even in liquid atmospheres and at different temperatures. This is not a paper done with the Synergy ED, but we have the same capabilities in our instrument as well, again, by means of those specific sample holders, which are going into the goniometer. For example, to do these environmental chambers like liquid or gas environments, you typically encapsulate your sample in silicon nitride membranes, which have a high tensile strength and are electron transparent. And now I want to focus on one paper, again from the area of pharmaceuticals, which I think highlights quite nicely typical advantages and properties of electron diffraction. So this was about levocetirizine dihydrochloride. It's a common antihistaminic, and the structure is in fact unknown because this doesn't recrystallize to large enough crystals for single crystal X-ray. So in this study, what we did together with collaborators from NYU Abu Dhabi was to take a pill from a local pharmacy and grind it down. And now if you take this pill and just grind it, what you will see in the powder diffractogram is, it's lactose. This is mostly sugar. But now using, in this case, semi-automatic data collection from the individual grains in using micro-ED, we could quite easily and quickly find the needle in the hay, so to say, and find API crystallites among all those fillers. And with this, in a very straightforward way, solve this structure which has remained elusive for really long. And I think this highlights that it would be not doing ED justice to understand it as a pure single crystal technique. In an ED sample, you have thousands of grains. Even if you have only like microgram or less amounts of sample, they can be impure, polyphasic, any kind of messy. The acquisition per grain, the acquisition time is less than 2 minutes or even faster, even significantly less than 1 minute if you push it hard. And the collection can be automated. So typical modern ED schemes, and I mentioned this earlier, are automated in a way that you just take whatever you have from your synthesis or even just from grinding a pill, that can be a mixture, you put it on the grid, you have then the diffractometer measuring all the crystallites, or let's say many crystallites, and then automatically distribute this into bins with the different compounds and solve the structures from it. So micro-ED is not only a single crystal technique, it's also powder diffraction grain by grain. Another thing that we did in this study and many others is that we solved the absolute structure. and determine the stereochemistry of this API. So how does this work with electron diffraction? Here again, dynamical diffraction comes into play. There's no sizable anomalous dispersion with electrons, but you again have this inequality between the intensities and the square structure factors. I've talked a lot about this inequality, but you also have this one. So the free dynamates will not be equal anymore due to these dynamical effects. And that means that you suddenly get the information about the stereochemistry. If you do a kinematical refinement where you assume that all of those are equal, you have no way to distinguish those two structures from an electron diffraction dataset. But if you model it at the level of dynamical diffraction, the absolute structure is accessible, because if you refine this or that model against the experimental data, you'll get different R values. And by comparing them, you will see which one is the correct one. And then there was this seminal work by Clara et al. And the group of Lucas Palatinos, and they compared 58 or investigated 58 cases of chiral molecules, and just comparing R values gave you the correct one for all of those cases. Here you see an example from a paper that we did from a common antibiotic, and it also worked nicely. There's a more robust and quantitative metric to assess the confidence of this absolute structure determination, which is a Z-score. I don't want to go into detail how to compute this, but this is really a nicely unbiased way of quantifying the confidence of your absolute structure determination. Once you have a Z-score of larger than 3 sigma, you can be more than 99.7% confident that you got the right one. And more often than not, you will find that for typical molecules that you study in the electron diffraction, it's quite easy to exceed that 3 sigma, even with data of, let's say, modest quality. You don't need particularly great data for that. Now, another pharmaceutical application where these properties of electrons came in handy, and here I'm now referring again to how those structure factors scale with the atomic number, is to determine whether a certain crystal structure is a salt or a co-crystal. And this was studied in this paper by Spera Pharma in Japan, also using Synergy ED. And they investigated for 3 APIs whether they are salts or co-crystals, just by refining the position of hydrogens to see if the protons actually have been transferred or not. Here you can see that they found a co-crystal just by comparing those distances. Another case was also found that it's a co-crystal. And finally, here it was seen that the protons are closer to the nitrogen, and it could be inferred that a transfer happened, and we have a salt here. Now, finally, I would like to mention that micro-ED is absolutely possible. It has to a large extent also been developed for the case of proteins. It also works very nicely under Synergy ED, as shown in this paper, and also runs the normal Chrysalis Pro pipeline. The bottleneck at the moment, I would say, for protein micro-ED is that sample preparation is still quite hard. You need to get these small crystals either by crushing larger crystals or using focused ion beam milling, or doing work like in vivo crystallization. So it's a bit tricky. I can highly recommend a paper up here, which is quite recent, from Tam Yangonen's group about sample preparation, which discusses those challenges and how to overcome them. So do you have any questions for now before I move on to the Outlook section?
Yeah, we have quite a few questions now stacking up. So let's try and take maybe 3 or 4 of them just now, and then save the rest for the end. So going back to the cryo transfer holder, is the holder suitable for all air-sensitive materials?
The cryo transfer holder, you mean for air-sensitive materials? Well, if you can come up with a workflow where you would transfer, well, let me fire up that slide again, where you transfer this sample into the holder inside a glove box, then you can make a reasonably air-free transfer because this environment here will be filled with dry nitrogen. But the primary task here is to protect rather vacuum-sensitive samples, not necessarily air-sensitive samples, but we also have specific holders for air-sensitive samples, which work in a similar way, just that for those, you will really have a hermetic seal here. So you have an O-ring seal at the tip, and then you can retract your grain into the holder where it's perfectly sealed inside an inert atmosphere and get it then into the diffractometer. So for optimal air-free transfer performance, you can have even different holders, but even with a cryotransfer holder, you can be a bit creative and handle very nicely air-free transfer and air-sensitive samples.
Okay, thank you. So what is the maximum tilt angle, and do you have a completeness issue for low symmetry crystals?
So in the Synergy ED, it depends a bit on the particular sample holder you're using. So you see, depending on this thickness here, they may shade some parts of your sample. But for example, for room temperature measurements, we can tilt plus 80 to minus 80 degrees, so a total range of 160 degrees. And this one is a total range of 130 degrees. And this is typically enough for ab initio solution up to monoclinic data. So we get completenesses of the order of 70-80%. That's enough. The triclinic data, what you will usually need to do is to merge data from various crystals with slightly different orientations. We have tools for that. This is actually a slide I was going to show later on, but it illustrates that, I think, the best. So we have data management tools where if you collect from many crystals, you just see what you did. You see the unit cell to check them for compatibility. You can even apply some sort of clustering if you had mixtures. And then merge together these different data sets that all belong to the same compounds and then solve the structure from these compound data sets. And with this, we can even quite easily solve triclinic structures. For example, this one, this monster here is triclinic, and also some of the natural products we've looked at. It's not a significant problem.
Okay, shall we move on for now and pick up the rest at the end?
Sure. So just a very brief outlook about some ongoing topics and developments that we're doing right now. So once more, I want to highlight the ability of electron diffraction to screen a large number of crystals and making this effectively a powder by the grain technique. And by now, you don't have to do this anymore manually. Now in the Synergy ED, and I think also in some other systems, we have quite powerful tools for just automating this process. So you don't have to sit in front of the diffractometer anymore and center each grain manually on the rotation axis and then do a measurement and then move to the next one. But you can run these experiments in an unattended way. The instrument will automatically do the height centering of your crystal grains on the gonio axis. This is actually what you see when it switches to this red color map. It activates this mode for automatic centering and then collect from them. Now this video is running at increased speed. It's not quite that fast yet, but it's in fact a focus of R&D right now to make it much faster and really go to a throughput where you can screen hundreds of crystals easily without within hours or even 1 hour. And now getting back to this slide, this is of course especially powerful if you have multi-component systems. So we have powerful data management built in. And this is another area that we're working on more and more, is how to automatically work with these multi-component data sets, for example, using automatic clustering, which we have now built in Chrysalis Pro, that can assign each crystallite to a certain polymorph or even different constituents of the samples. This example is from a clinker, so which is multiphasic like crazy. And even in this standard system, we found an unexpected crystal system when we measured this for with electron diffraction instead of powder XRD, which was quite a surprise. And as I've shown already, if you have those compound data sets, you can also just solve structures from them by merging data from compatible unit cells and then getting structures from those compound sets. Also, this is all embedded into the workflows in Chrysalis Pro. And then finally, one development that I find quite exciting is can we actually do micro-ED beyond pure crystals? And here I want to show some results from battery material, so from an NMC cathode. And I should highlight that we also will have one episode of this webinar series by Josh on battery materials. And here we see diffraction, total diffraction signal, reciprocal space reconstruction from a pristine material and from a cycled material. And you see that in the crystallographic pipeline, you still get nice lithium atoms here, which are intercalated between the NMC layers. But you see that the diffraction signal deteriorates a lot. And what we're working on quite a bit right now is to understand this total scattering and to understand defects and disorder better from the diffraction signal we're collecting. And then in a related way, also look at fully amorphous or partially amorphous samples and look at pair distribution functions. And the advantage you have with electrons there over powders is that you don't have rotational averaging. So you can have 3D pair distribution functions in the coordinates set up by your crystallographic directions on individual grains to quantify short-range orders using techniques like 3D delta PDF. This is also a very active field now within the scientific community of electron diffraction, and we're also working on this quite a lot at Rigaku. So let me conclude with some take-home messages. Micro-ED or 3D ED has now evolved from an exploratory approach to quite a mature tool that has entered the toolkit of structural characterization. You can get accurate structures from submicron crystallites without having to tediously crystallize large crystals or recrystallize compounds. With it, you can solve everything that is nanocrystalline, and then using these approaches that go beyond the crystallographic pipelines, even beyond, and you can do this not only in vacuum, but in different environments. And then, because it's essentially a powder by the grain techniques, you can analyze native and impure samples and get a full structures out of it still for cases where this would be absolutely infeasible with powder XRD. So if you have a messy powder, you will not only learn that it's messy, but you will also learn what really is in there. And then with the dedicated diffractometer, all of this becomes pretty much as easy as conventional techniques without the need to also know anything about microscopy or other electron-specific techniques. And with that, I'm done. So please shoot away with all questions you still may have.
Okay, thank you very much, Robert. That was a really nice presentation. We do have some more questions, as I said. Let's try and handle some of them before we wrap up. You just kind of slightly touched on the first one, which is why is a dedicated diffractometer better than a TEM?
Okay, so I would say if you are, let's say, if you buy some diffraction-specific attachments to a TEM and you are a highly skilled crystallographer and microscopist who knows how to set up a TEM properly in a bit lengthy procedure, you can get as good ED data on a TEM as on a dedicated diffractometer. Now, this was a lot of ifs. Because you're really coercing an instrument that's made for something different into something that it's not made for. In dedicated diffractometer, you have electron optics, which is really optimized for the task. So you can allow, for example, for a much larger, let's say, sweet spot of parameters for the illumination and for the detector distances that will still give you excellent diffraction data. Whereas for electron microscopes, usually you have a very narrow range of settings where this works nicely. Also, usually you cannot rotate your sample to as high angles because there's just too little space in the confined geometries of thin pole piece gaps of high resolution microscopes. And then I think, and this is from a practical perspective, maybe the most important is that even if the hardware is similar, the control system and user experience are very different. So in our Synergy ED, we do have a lot of parts from our friends at Geol, but we're completely replacing, let's say, the operating system of the whole instrument, of how the hardware is handled, and change this to something that's specific to electron diffraction in a way that the stability is always ensured, that lens currents are set in a way that the stability is not compromised, and above all, that you have a full crystallographic pipeline, full crystallographic workflow without having to stitch together a lot of different software and hardware components.
Okay, thank you. So this question, I'm aware that samples suitable for ED need to show Bragg reflections above 25 degrees to theta using copper K alpha radiation. What is the reason for that?
Well, this is, let's say, just a rough guideline. And what this basically says is it is still a crystallographic technique, and except for these cutting edge applications like pair distribution function, total scattering, you just need your samples to be crystalline in the first place, and you need to have diffraction to at least, let's say, 1.2, 1.3 angstrom to have a chance with a structure solution from single crystal analysis methods. This is basically what's behind that rule of thumb. Of course, you can still try with anything, but you should still see at least some lines in powder pattern. Otherwise, you might just be wasting your time.
Thank you. So could crystals on the mount be mapped on the grid in 3D space that could be taken into account when planning diffraction, similarly to single crystals?
I'm not sure. Can you repeat the question? I'm not sure getting that one.
Yeah, could the crystals on the mount be mapped on the grid in 3D space? And then could that information be taken into account when planning diffraction similarly to single crystals?
You mean if we look at the morphology of the crystals and
I'm not sure what the asker is driving at, so maybe they can follow up just to clarify while we move on to someone else.
Yeah.
Still not sure.
Yeah, maybe so. But just maybe generally, if this refers to crystal morphology, that we could look at just like in an X-ray diffractometer. This often doesn't help you very much for these nanocrystals. They just often look very wild and don't tell you much. And then if it refers to something like a pre-experiment that you would do with X-rays, there's not really much you can do because you don't save much time compared to doing an actual experiment, even more so as determining the, let's say, the UB matrix, so determining the unit cell and the orientation of a crystal already needs a collection of a wedge of at least, let's say, 30 degrees, owing to the fact that the Ewald sphere is so flat and that in small wedges you only get two-dimensional information.
Mm-hmm. So when I read that question, I'm thinking that it's pointing towards automation and locating the crystals on the grid for later doing diffraction, maybe.
Oh yeah, well that's a different story. So yes, hell yes, of course.
Yeah.
So in fact, these annotating those crystals here is something that can be done automatically using image processing. And there are various algorithms available. We also are investigating this and do have, let's say, an early alpha version of this in the Synergy ED that you can use. But we are already anticipating and doing a lot of R&D in that direction, that machine learning will boost that a lot, the efficiency of the selection of grains from this in the first mapping step.
Okay, so the asker has followed up the morphology or the possibility of multicrystalline scattering from other crystals during rotating?
Yeah, so yeah, but basically that would amount to, let's say, understanding the whole 3D arrangement of those, and then how likely it would be that they would overlap at some point. And yes, this can totally be done, understanding those environments.
Okay, so we're already 5 minutes past time, so I think we should probably pick up the rest of the questions offline. I just wanted to make a few little advertisements at the end, if I can just quickly share my screen. So firstly, I just wanted to point out that the next edition of this series will be on the 7th of May at the same time, presented by Jessica Birch. So please do join us for that. This will be covering the sample preparation, as Robert has already mentioned. And we also have two related events upcoming soon. So the first is the Northwestern Rigaku Symposium, which will have some electron diffraction, again presented by Robert, as well as some other of our users. And that will be on the 22nd and 23rd of April, so it's not far off. So if you're in America and you want to attend that, then please visit this page. I'll paste these links quickly into the chat as well. And then the last one is the Yale Symposium, which will be on May the 28th to 30th at Yale University. So again, if you're interested in registering for that, please do. So please do join us for those events. And again, thank you, Robert, for the very nice presentation. Thank you, everyone, for attending, and we hope to see you at the next edition in the series. Thank you very much, and goodbye.
Thank you. Bye.